Let us now start with counters. Counters are circuits with several states, and in this picture or the state transition diagram, each state is represented by one circle here. This is state 1, this is state 2, state 3, 4, etc. up to k. And after this state, the counter goes back to state 1. And this kind of counter with k states is called a modulo k or mod k counter. And what is inside a counter? Let us see. A counter can be made with flip-flops, each flip-flop serving as one memory element with two states, 0 or 1. The output of the flip-flop Q can be 0 or 1. And if there are n flip-flops in the counter, we have 2 raised to n possible states, because each flip-flop can have Q equal to 0 or Q equal to 1. And therefore, let's say we have 3 flip-flops, then we can have a maximum of 8 possible states here. So our k can be 8. But we can also exclude some states, and therefore n flip-flops can be used to make a mod k counter with k less than or equal to 2 raised to n. So that is what this picture shows. Inside this counter there are flip-flops, and this Q0, Q1, Q2, etc. are the outputs of those flip-flops. And how does the counter go from one state to the next? For example, from 1 to 2 or 2 to 3. That is done by the clock pulses. So every time there is a clock pulse, the counter will advance by one state from 1 to 2, 2 to 3, 3 to 4, and so on. And this goes on. In addition, a reset facility is also provided, this input here, which can be used to force a certain state to initialize the counter. For example, let's say we have 3 flip-flops inside this counter. So the outputs are Q0, Q1, Q2. And we might want the counter to start in the state 0, 0, 0. So that can be achieved using the reset facility. Now in addition, there is also this box called decoding logic shown over here. We will look at that a little later. Here is an example of a counter. This is the general state transition diagram, and this is our specific counter. And in fact, this is a circuit we have already looked at earlier. So the sequence for this counter is shown over here. If we start off with Q0, Q1, Q2 equal to 0, 0, 0, then this is how it proceeds. And here is a table showing Q0, Q1, Q2. So we have 0, 0, 0 to begin with, that is our state 1, that one. Then we have 1, 1, 0, 1, 1, 0, that is our state 2. Then 1, 1, 1, 1, 1, 1, state 3. Then 0, 1, 1, 0, 1, 1, state 4. Then 1, 0, 1, state 5. And then after that, we come back to 0, 0, 0, back to state 1. That means our last state, this one, is 1, 0, 1. So k here is 5. So it is a modulo 5 or mod 5 counter. Let us now look at this decoding logic. This logic is nothing but some combinatorial circuit suitably designed so as to get some desired outputs here. Could be one or more outputs. Now, since the counter is cycling through k states, these outputs will also be periodic. That is, after k clock cycles, the output at any of these pins is going to repeat. Now in particular, let us take this example. Let's say we have a mod 8 counter, that means k is 8. That means we have 8 states, 1, 2, 3, 4, 5, 6, 7, 8, and then back to 1. This is our clock signal. Now it should be possible for us to design our decoding logic so as to get this kind of waveform at one of the output pins here, for example the first one. Now this signal X is 1 when the counter is in state 3, otherwise it is 0. And since state 3 comes once in every 8 clock periods, if the clock period is T, this interval is going to be 8 times T. Or in other words, the frequency of this signal X is going to be the clock frequency divided by 8. So let us make that remark. It is possible to have a decoder output, say X, which is 1 only for state I, in this case the third state, and 0 otherwise. So for k clock pulses, we get a single pulse at X, that is, the clock frequency has been divided by k. And for this reason, a mod k counter is also called a divide by k counter. So this counter, for example, would be called a divide by 8 counter.